Okay, so starting a few minutes late today, but that's all right. So you had a homework assignment due today? Mm-hmm. Wait, I think I have some homeworks back, actually. Do I owe you some homework? I do, and here it is. Pass those around. Okay, and then for today there was a homework assignment due. I think it was to do some finite state machine designs and maybe eliminate some empty transitions or something like that.
Yeah.
Mm-hmm.
Mm-hmm.
No questions? I thought there were questions.
Can a deterministic finite state machine have an empty transition?
No. If it has an empty transition, that by definition makes it a non-deterministic. It makes it, by definition, makes it non-deterministic. A non-deterministic, remember, a non-deterministic machine is one that has, for example, if you have a state here, you would have two different transitions on the same letter, on the same terminal character. So like if this, you could go from here to here on B, or you could go from here to here on B. So therefore, the reason this is called non-deterministic is because it's not, if you're in this state and the next letter that you're going to scan is a B, it's not determined whether you should go this way or this way. That's what makes it non-deterministic. And by the same token, what happens is if you have a transition on an empty, if you have an empty transition in your finite state machine, that's also non-deterministic, because given that you're going to scan a B, you could either scan a B and go, or you could go here and not scan anything. So this, by definition, gives you a choice. You see what I mean? Mm-hmm. By definition, it gives you a choice as to which transition to make. Mm-hmm. And so any finite state machine with an empty transition is by definition non-deterministic, as well as a machine that has two different transitions from the same state on the same input character, terminal character. So I think the one for today where you were supposed to design some finite state machines, mm-hmm. they had to be non-deterministic.
No, they had to be
It says deterministic.
Sorry, I said that exactly the opposite. They had to be deterministic. Yeah. They had to be deterministic.
That makes it a little difficult.
Yeah, and the other thing is, did I tell you about the number of states?
4.
Yeah.
Site, yeah.
We're not allowed to have more than 4?
Well,
For all of them.
I want you to use the minimum number of states, and in that, and I'm telling you.
You have to at least have the 101, which is 3 transitions.
Exactly, so you're right. Mm-hmm. Right.
So can you use more for the following steps? Or for the following ones? Or just...
What do you mean the following? What do you mean the following ones?
For each one?
4 states for every problem.
Yeah. And it is possible to do. I would not tell you to do ask you to do something that was impossible.
On the deterministic ones though, so like each time you're going from one state to another, do you have to have the option to do like both things in the alphabet? So like from going from like A to B, do you have to have a 0 and a 1 someplace? Or can you just have one thing?
Like if
You
the
don't have to have
0
both.
leads to a non-accept state, do you have to show that?
Oh, so, well, okay. I think, is your question related to the fact that whether we're doing a simplified?
Mm-hmm. No, it was the one where you're drawing, like having it end in 101 or something.
You're asking if we can draw a simplified diagram.
Well, I mean, it's, okay, all right, I'll say 2 things about that.
Mm-hmm.
It would be legal for you to draw a simplified finite state machine, but I will tell you that in this exercise, none of them. Yeah, I mean, you have to have.
Well, the first one, but.
Oh wait, I'm sorry. Maybe the first one.
Some of them
Yeah, you're right. I'm sorry. The very first one was just to recognize
do just 1 0.
just do 101 and that's it.
Yeah.
Yeah, I'm sorry. That one, a simplified one, would work. But I think in the other ones, I don't think.
Well, there's another one that says it has to start with 101, and then it can be anything after that.
Oh, I'm sorry. You're right. That could be. Yeah, I'm sorry. You could write a simplified one for that one too.
And the other two?
I'm being proven wrong on all of that.
Like, do we have to have this?
Do you want individual arrows
Why?
for...
Because it's going to.
For example, if one is going from
Because
one
this
state
should
to
be
another.
accepted.
Yeah. So here, what you're asking is this.
Be accepted. If you didn't have
Suppose you can go from here to here on a 1.
Can I draw?
If you want, but also on 0, what you're saying is, do I have to draw it like this, or can I draw it like this? 1, 0. And the answer is you can draw it like this.
Can I also put an arrow on the opposite end to show that they can go back and forth?
No.
Oh, okay.
Would have to draw another
Separate.
arrow?
Yes.
Go opposite direction.
No, no, never. You never ever see double-headed arrows on finite state machines.
So if there's like
I've never seen that.
if there's a self loop, like,
Yeah, there can be self loops.
but can you do 1, 0? Or can you draw 2 separate ones? Does it matter?
Well, like this, if you wanted, if this can go to its, if this one can go to itself on 0, 1, you get to say 0, 1.
Is it wrong to draw both zeros?
No, but I mean, you normally want by the same token, you know.
Yeah.
Here's what I recommend you do on parts. What were there? 4 parts? A, B, C, and A, B, C, D. On the last 2, what I recommend you do is I recommend you consider what the effect would be starting at any state if you have a 0 or a 1 from that state. And what does that tell you? See, the thing of it is, you guys, is that there's no recipe that will say how to design this machine to recognize this thing. It's a design problem, and like all design problems, there's an infinite number of ways to do it, or maybe not infinite, but well, maybe infinite in some cases. Maybe infinite in some cases. So most design problems have an infinite number of solutions.
So there's no like strategical or like analytical approach to this. You just have to kind of.
Well, yeah, there is. Yeah. Actually, I take that back. I mean, there is some, you know, I don't know how many of you guys, I don't remember how many of you guys are in automata theory right now, but just okay. But there are actually ways, there are systematic design approaches that we just don't have time to get into. So this is you know, kind of like your first sort of like ad hoc. You're just approaching this in sort of like an ad hoc way. You know, like in the computer organization course, remember how we're doing systematic design, digital circuit design techniques, and there are systematic ways to approach a design that do the tables, and there's a way to do it. And there are principles like that in finite state machine design, and what you have to do is each state has associated with it of what it is that you've recognized to that point. But if you just think that through, you should be able to come up with the correct design. Think about it here. Think about this. Like when you get, well, you know, like, you know, if you have a design like, if you have some sort of a design like this, and maybe this is a final state, just think to yourself, if I'm in this state, what have I recognized? And then if the next character comes along, what do I know? What have I recognized so far when that next character comes along? And ask yourself the question, well, if that next character comes along and I'm wondering where I should go from this on a 0 or on a 1, think, well, what do I know has been recognized so far? Ask yourself that question, and that should tell you where to make the transition to. This exercise, I really don't want to say too much more about this, because I think this really is a good one to help you do some independent thinking, analysis, you know, sort of like thinking.
It's toughy.
It's kind of tough when you see this for the first time. And I know that whenever I ask a question like this, there are frequently designs that where students don't take into account. Well, let me say it like this. It's easy to design a machine that will recognize what it is that it's supposed to recognize. It's more difficult to make it not recognize something that it's not supposed to recognize. In other words, usually what happens is the machines recognize too much. They recognize what they're supposed to recognize and even more and more. And usually what happens when I grade these is I say, oh, Yeah, it does recognize this, but it also recognizes this, and it
Too
shouldn't.
accepting.
They're usually too accepting. Right. So you have to think through, yeah. The key, like if this is coming in here from the start. The key thing is, at least in parts C and D, the last two parts, the key thing is when you get to this state, and you know that if you get something you'll go here and something you'll go, but what if you get what's not? If you're in this state and you don't get this character that's going to get you to the goal, and you get another character, the question is, well, now that I've got this other character, the way you analyze this is you say, well, now that I've got this other character, what do I have so far? And is what I have so far something that's going to help me get to my goal? In other words, frequently you don't want to go all the way back to the beginning and just start all over, because you might, even if you get the wrong character and going from here to here, you might still be, well, you might think to yourself, well, I know that if I'm in this, how did I get to this state? The only way I could get to this state is if I went from here to here.
And when it asks,
See what I mean?
or when it says like a string of arbitrary length that ends in 101, that arbitrary length could be nothing, right?
It could be nothing.
So it's just
Yes,
one.
yes. And the key there is to do the shortest one,
Right. Okay.
which I don't think I'm giving away anything if I say that would be a 1 here, and a 0 here, and a 1
you
here.
figure out the other.
But then the tricky part is figuring out the other ones. Like if if it's a 1 and going from here to here, and a 0 and going from here to here, the question is, if I'm here and I get a 1, where do I go?
Where do you need to go? Yeah.
But then you say, well, where do I have to go? Well, how do you know what happened when you got here? You got here from here. And usually there's a tendency to go all the way back to the beginning unnecessarily. I'll say that I think that's enough. That's about as much as I'm going to say.
Oh, we could have started with statement? Oh.
You were supposed to start with statement. Because it said,
Is that noted somewhere?
yeah, it says show that it is a valid statement.
Oh, okay.
Yeah.
No, that was a lot larger than I...
It was a little
I
larger.
started with trans...
Right, you started with a translation unit. Yeah. Okay, are there any more questions about the homework? Okay, well, you can hand those in now if you'd like, or you can wait until later if you need to. Is all of this pretty easy? And with see, what normally you're taking things out of sequence.
Yeah.
Normally.
Doing automata.
Yeah, I know. And so she's had this. Yeah.
Like we draw it.
Every single day, and exactly. Yeah.
And they're pretty, we know about
And no,
five
but
per month.
yeah. So, but you're taking things out of sequence. You've always done that since the beginning, because you've been, you got started late, and then we're doing this and this at the same time, and anyway. So, but that makes it easy for you. At least maybe here you're going to see a more practical application that you would not see in the theory class.
Well, the epsilon transitions was different. We didn't do getting rid of epsilon transitions.
Oh, I'm sure you will.
We did switching from an NFA to a DFA, so we just did kind of a much more complicated version.
Yeah, but I mean, I would think that you would do empty transitions and eliminating empty transitions, because there's a systematic procedure for that.
Because we did the whole DFA to NFA to algebraic expression
Yeah.
or logical expression.
We did the NFA to a DFA was just really complicated, though. That was where you had to look at each state and make.
Yeah, and then make it a states of states, right.
So I think it was
Yes,
encompassed in that.
yes, yeah.
It was part of it.
Yeah. Anyway, this is all practical. The purpose of this is to introduce you to that. Normally you take this first, and it's to introduce you to this and show you the practical application. And then now the other thing we're going to do is we're going to program one, which you don't do in the theory course.
I feel better about being a little bit confused at the beginning of automata.
Oh, because when you started,
like trying to pick it up real quick, and I was
yeah.
wait.
But yeah. See, if you had seen this first, then yeah.
Can I ask have
Okay.
a question about the, when
Sure.
you're taking out the epsilon.
Yes, when you're taking out a, so like here, if you have a state from here to, if you have something from here to here, and from here to here, and this is on this is epsilon, then, and if this is like with x, then what's your question?
Okay, my question is, there's one where like the epsilon goes from one state to there, to like that one, but then that one goes back to the other one.
So back to the
Back to
initial
what?
state.
Back to the
initial.
Oh, interesting one.
So I would feel like there'd be a self loop on both of those, but is it incorrect to have it on both of them?
It is incorrect to have it on both of them.
So which one would you do it
Well,
on?
which one do you think?
The second.
Yeah. Oh, no, hold on. Wait. What do you in this case, oh, here, let's make this y. In this case, what do you do? Instead of going instead of going on the empty transition from here to here, and then on y from here to here, you could just as easily go from what on what?
From there, so-
From here to here on what?
Y.
On y. So, think it through. If you could go from here to here on the empty, and then from here to here on x, that's the same thing as going from what?
From x to x.
From, well, here, let's call this a.
I don't know what to
Yeah, let's say,
A on
okay, so here, if instead of going from A to B on the empty and B to C on Y, that's the same as going from here to here on Y.
Right.
But wouldn't the validity, wouldn't it be irrelevant? Wouldn't it be irrelevant? Say you had a self loop on A and B for X, wouldn't it still be the same grammar?
Because you're gonna have
The
to have
same language? No, hold on. When you get rid of this, you got to replace it with the transition from here to here on Y. But then you also have to, because you can go from here to here on the empty and from here to here on X, that's the same thing as being able to do what?
Go to A,
Going from here to here on X.
but wouldn't you still be able to do that on B to, from B
Couldn't
to
you
B?
do that from B to B though?
So say you,
Hold on, wait. Okay, there's two things here. First of all, B may be, after you get rid of this empty transition, B might be unreachable.
And that's okay.
Yeah, and that's okay. But
because the states aren't really important as long as the grammar's correct, right?
oh wait, I think I just skipped ahead about unreachable states.
Inaccessible.
Did we have, inaccessible?
Yeah, we had it on
That was
homework.
our homework.
We had that, okay.
But
But hold on, when you do this, it might be the case that B is inaccessible, all right? But by the way, the other thing we remember is if B is a final state, then what has to happen? A has to be a final state.
No.
yeah, we did.
You want your paper back? You want your paper back?
So this needs to be a final state.
Did you remember that? You know, I get people who complain about, critics of my book who say this stuff doesn't belong. They say, why is this chapter in computer systems book? To me, it's the heart of it because we're talking about languages and languages in between levels of abstraction. To me, it's
They're saying you shouldn't talk about finite states.
machines, yeah, or all this grammar stuff. It's weird.
Yeah, that
that
doesn't make any sense.
it doesn't make any sense that it shouldn't be. I mean, you'd think it would have to be in there.
Yeah.
It's just the natural.
What would they replace it with?
Nothing. They do computer systems, they don't do any of this stuff. Which seems to me so unnatural, but that's the way it's normally done. And to me, it's just a natural thing to have this finite state machines in here. Because every level of abstraction has a language. And the most important, and it's not important just what happens at a level, it's important what happens between the levels. And so, you know, you've got a language at this level and a language at this level. And so you got to be able to, language translation between one level and another, it's natural to have it in. Anyway, go ahead.
Just a question about or final states.
Yes.
Are you able to have a loop on a final state?
Yes,
that
you are.
Might not even be used.
We were just talking about it for like 5
Well, what do you mean not
Well,
be
because
used?
if you get to the final state in one way, it could just end there. But then if you want to loop on the final state,
Oh, right, yeah, yeah. There can be strings. There can be strings that end on that final state without taking that loop, and there could be other strings
Okay.
that end there. But if there is a loop to itself, then it could.
use 'em.
Yeah, it could. Yeah, it's not a prerequisite that every string has to use every transition, you know, to be recognized. You know,
You
so
took
yeah.
C, and then you took epsilon, you'd be in C. Only
Are you stumped?
I'm still confused on this one.
Well, what's your question about this one?
If you're in B and you take X to A,
But you're-
then you take.
Hold on. We're talking about eliminating the empty transition.
Yeah.
So if you're starting in B, there's nothing to end the empty. That has nothing to do with eliminating the empty transition.
You don't need a loop on B of X?
look at the top of page 350.
No. To eliminate the empty transition from here to here, what you have to consider is if you start at A and go to here on the empty transition and then go from B to C on Y, then that is equivalent to starting from A and going to C on Y. Because you're scanning that one, because in the first case, and going from here to here, you're not scanning it, and then going from here to here, you'd be scanning the Y. So you don't. So to do this, you would go. So to eliminate here, to eliminate this empty transition, what you would do is you would go from here to here on Y, and then from here to here says you could go from here to here on empty, and then from here to here on X. That's the same thing as going from here to here on X. Are you right? Are you with me there?
And if B was
So with this X, and then you eliminate this.
and if B was a final state, then A has to be one of
And if B were a final state, then A would have to be a final state. And that's it.
So what if you had another way to get to B? What if there was a fourth state?
Yeah, that's fine. Yeah, if there's some other state over here, and there's a way for it to be on like on like G or something like that.
Then would you need a loop on B?
No,
With X?
no.
But shouldn't
No.
GX
If A
Y?
is
No, because if you're scanning G here, if you're scanning, like F, G, C, or something like that. If you're in this state and you scan a G, boom, you go here. Right.
Oh, it's unnecessary.
if A is going somewhere on an empty string,
On an empty
on
transition.
an empty transition, if you want to go to the empty transition, then A just has to be able to go everywhere that other state was able to.
Everywhere from which you could get from this state.
Yeah.
Because you could go from here to here without scanning anything. And then you could go from here to wherever else from all the other ones, like from here to here, from here to here. So you have to include those on going from A.
Right, but what if there was a state before A?
All right, so what? So here's A, B, C, let's have this be D and have this be capital E.
So would E have to go to B on X?
No. Why?
Because if you're eliminating it, can it?
No. Well, but when you eliminate this, what are you eliminating? You're eliminating the possibility that if you're in state A and you're at a position in a string, you can go from here to here without scanning anything, and then go from here to here by scanning this next letter.
So it has nothing to do with going from E. No.
No.
It only involves A, B, and wherever B goes.
Yes. Yes. I'm not sure I understand why you think it's necessary to consider these other possibilities to make an equivalent finite state machine. I don't. Why would it?
Because I feel like you could go from E to A, and then you could go from A.
Okay, watch this. Maybe we can do this with some specific ones. Let's say this is on lowercase a. All right. And let's say that our string is. A. Let's say that our string is AY. All right.
So that's why we made the loop.
So watch, and let's say that we're at this state E. Let's say that this is our start state, all right, and that our scan is AY. Then what happens is, here we are in our start state. We scan an A, that takes us to this, all right. Now, suppose it's before we eliminated the empty transition. So then we could take the empty transition from here and not scan anything here, right? And then on the Y go to here, so boom, that takes us to here. But now don't you see that that's the same thing without the empty transition as doing what? Going from here to here on the lowercase a, which takes us to here. Are you with me?
Yeah.
And then taking on Y to C, on Y to C. So there, that's now we're here after scanning AY. So that's why we had to replace this. That's when we take off this, we have to put this in here. So we can get from here to here on Y. Now, was that clear? You see what I'm saying? We were able to go from here to get to A, and then on Y, with the empty transition, we could go empty and then Y here, but or if we're here, we could go just Y to here without the empty.
What if we?
But see, that has nothing to do with how we got to there how we got to here in the first place.
So it has nothing to do with the states before it.
No. Well, I mean, do you see why? I'm just
Yeah.
you need to visualize how that machine works and see why.
It's more when we're coming back that I'm confused how we put the loop. Like, why wouldn't we have to have a loop on the B too?
I think you're just doing the same thing twice. Like doing that allows you to do the same thing a different way. And you don't need that. It's like doing it backwards maybe.
Yeah.
From state E, you can get to state A on A.
On little a, yes.
Now,
So like in here, so here, you imagine the little cursor is here, and we're starting at the start state, and here we have an A, so we get to here on here.
Okay.
Okay.
My question is, rather than do a state working with state A, could you draw a line using little a from state E to state B with the character A? Wouldn't that be the exact same thing? So, for example,
Oh, so what you're saying
going
is
from state
no. Hold on. Then what you're going to do is you are eliminating this.
right,
Yeah, but we don't want to eliminate those. We want to eliminate the empties.
but wouldn't the grammar be the same?
Okay. Wow. Okay. But you're making it more complicated.
But it's.
I don't.
Like,
Well.
on the homework assignment. would you-
No. I bet I could find one that it wouldn't be equivalent. I bet if you start going down that road, I bet I could find a counterexample of something that would recognize that the original one would not, or vice versa.
Okay.
Are you with me?
So just stick to the.
You stick to the recipe.
To the recipe.
That's. I would not advise going down that road.
Okay.
Are we good? Is everybody good?
So this one's not right then.
Oh, this is good. It's not that I hate to see you in pain, but
That's good.
but I do like for you to grapple. I think did that clear it up?
Yeah,
Good.
it's better. Just
Good.
follow the rules.
Yeah, just follow the rules.
Blindly accept.
No, not blindly. I'm trying to explain. It should be clear. It's not, the recipe is not blind. Here was the recipe, by the way. The recipe was this: removing. Given a transition from P to Q on the empty transition, for every transition from Q to R on A, add a transition from P to R on A, and then if Q is a final state, make P a final state. But I mean, I hope these examples that we did, like here, like this example figure 7.18, the example figure 7.19, the examples in figure 7.20, they all make sense. I mean, the recipe is just logic. It's just based on logic.
That's where I got that from. I get it now. I was doing a completely different method.
Well, I'm glad we spent this time to clear this up.
We are.
And we also have it for posterity. For those of you,
Just watch the video.
exactly. That's what I should do. Next year, I should just sit back and not even come to class. I should just come in here and just click, and put it up.
Email me if you have any questions.
Right. And then just leave.
But the research-
I don't think they would like, I don't think I'd get my paycheck very much longer after if I ever tried that. Okay, today we really do need to get to some new material. Okay, so today we're going to do multiple token in fact, you have a program due, I guess it's not till Thursday.
the program
So I guess we're in pretty good shape. Okay, so today we're going to do multiple token recognizers. Now, first we have to understand what is a token. And I'm not sure if you do multiple token recognizers in automata theory or not. Maybe not, maybe not. Because this is a very practical application. Now we're talking super practical application. Okay, so now, first of all, what is a token? A token, according to this definition on this slide, is a set of terminal characters that has meaning as a group. Now here I want to illustrate this definition with an example. Now you guys, we've done assembly language, we've done PEP8 assembly language, right? Now do you guys recognize this? Does this look familiar? Main, colon, decimal input, num, comma, D.
Yeah.
Does that look familiar?
Yep.
What is this, you guys? This is a string of what kind of characters? A string of what kind of symbols?
English
Well,
for assembly language?
yeah, but what are the 4 parts of a grammar?
No, non-terminals,
Alphabet.
What kind of alphabet?
non-terminal.
Non-terminal.
Non-terminal alphabet?
Terminal.
Terminal alphabet?
Production.
Rules of production? Da, da. What's a finite state machine?
Rules of
Set of
state.
nodes that are the states, and one of them is a start state, and one of them is a final state, and then the transitions between them, blah, blah, right? Okay? So now what is a token? It's a set of what? Terminal characters. So that was like the first part, no, it was the second part of the grammar, right?
Oh, cool.
Are you with me?
Yeah, so that's why all this work.
These are terminals. This is a string of terminal characters. These are a string of characters that are from the terminal alphabet, right? So in a grammar, these are the ones from the terminal alphabet. In a finite state machine, what are these? These are the symbols where?
On the lines.
On the yes, on the transitions. Are you with me? Is everybody clear on that? Okay. Now, what does it say? It says, let's take a look at this definition of a token. First of all, it's a set of terminal characters. Actually, I should have used string on that. I should not have used set. I should have used string.
Because second.
Remind me, yeah. I need to remind myself to change that. If it's that way in the book.
I
Hmm?
didn't get a typo on the video.
Oh, you need to tell me that.
I would.
Okay, so now let me give you an example. Check this out. Do you see this? Do you see this set of terminal characters? What is this set of terminal characters? It's AIN colon space D. Now, is this a set of terminal characters in this line? Oh, by the way, is this sentence in the PEP8 assembly language?
Yes.
It is. It's a valid sentence in the PEP8 assembly language. All right. Now, does this sequence of terminal characters? This is a sequence of terminal characters from this.
Yes.
Right? But do these have meaning as a group?
No.
No, they don't have meaning as a group. Which ones have meaning as a group? Well, this main followed by colon, that has meaning as a group because that's a symbol, the definition of a symbol. And then how about CI space N?
No.
That doesn't have meaning, but what has meaning as a group? DECI. Because that's a symbol that represents an instruction, right? That's one of the mnemonics. Are you with me? Does everybody see? Okay, so that's the definition of a token. In compiler, in translation theory, or in practice, a token is a group of terminal symbols that have meaning as a group. That's called a token. Are you with me? Does everybody understand? So it's a string of terminal characters that has meaning as a group. And so that's what a token is. Now, what we want is, and here's the problem. The problem is this. We've seen now how a finite state machine recognizes I want to say token, recognizes a sentence in the language, right? Do you see what I mean? In other words, we saw remember how an identifier worked? It was the first one is a letter, and then the second one is a letter or a digit, like that. So that recognized an identifier. Okay, but here's the thing, you guys. When we are translating whenever your assembler goes by and has to translate this, here's the thing. You don't know if the next thing coming up is going to be a symbol followed by a colon, or if it's going to be a mnemonic, or if it's going to be what is this? That's another symbol. It's a symbol. Or it could be this. How do you know when you get to this point if it's going to look like this or if it's going to look like this? 0x0001a, comma d.
As soon as you don't have a 0 at the beginning of it.
Well, I know, but when you're at this point, you don't know if what's going to come up is going to be a symbol or if it's going to be this, or it could be this. It could be like a 13, comma d. Do you see what I mean? If you are at this space, because what are you doing whenever you translate? You're scanning the input string one terminal character at a time, yeah? And the problem is, when you're at this one point, you don't know whether you should be looking for this, or whether you should be looking for this, or whether you should be looking for this. So what do you have to do? You have to design your translator such that if you're in this spot, what should you be able to do? You should be able to handle either this token, or this token, or this token.
Not deterministic.
Well, not necessarily. I hope not.
No.
Well, yeah, that's a good question. Maybe non-deterministic. Oh, actually, that was a good call. So, do you see? This is what we mean by a multiple token recognizer. When you're at this spot, you don't know whether you're supposed to recognize this or this or this. So here's what we have to do. We have to have a way to design a machine that will do any one of these three. Do you see what I mean? Because we don't know what's coming up next. Could be this, could be this, could be this. And the rules for recognizing this are different from the rules of recognizing this, different from the rules of recognizing this. Yeah? So look, what we need is, we need to be able to design a multiple token recognizer. That is, we need to be able to construct a finite state machine with multiple final states. And the final state determines the token that is recognized. So what we'll do is, in a situation like this, what we're going to do is we're going to recognize we're going to design a finite state machine that, in this particular example, it would have three different final states. It would have a final state for recognizing this, and a final state for recognizing this, and a final state for recognizing this. And what we want to have happen is, whenever we go through and get this next terminal character, that's going to make a transition, and the next one will make a transition, and the next one will make a transition, and boom. And then when we finally get to the end of that token, we want to say, oh, if I'm in this state, I've recognized this. If I'm in this other state, I've recognized this. If I'm in this third final state, I've recognized this. So the particular final state that we end up in will be the final state that recognizes one of these three alternatives. Are you with me? Now, the example that we have here is figure 7.21. All right? Now, here, this 0x, we know in assembly language, this 0x means what?
Hex.
Means what follows is a hex. Yeah, okay. The next. Okay, so here's what we want. What we want is, we know how to recognize the string 0x. Are you with me? How do you write, if I ask you, construct a finite state machine that would recognize the string 0x, what would it be? It'd be just like figure 7.21a, the top one. You would start at the first state, and then you'd have a transition on 0, and then you'd have to state B, and then you'd have a transition on X to state C. Actually, it would be even a little bit more complicated than this, because the X could be either uppercase or lowercase. Because you can do uppercase or
So you just have
uppercase.
two transitions.
Well, yeah, or a transition from B to C on either uppercase X or lowercase. But just to keep it simple, suppose we wanted to be able to recognize this. But then we also wanted to be able to recognize like the 1, 3. Because see here, we want to be able to recognize their X, or we want to be able to recognize the 1, 3. See? So now, how would you recognize, a digit? Well, you would go.
One transition.
Yeah, in one transition, the first transition from D to E, a separate machine, a separate finite state machine. So you would have a transition from D to E on 1.9. And then
it can't be 0.
It can't start with 0. Yeah, now actually,
that makes sense for decimals, I guess.
it does make sense, and the reason I did this is because, actually I don't think I've mentioned this before, because we use hex as opposed to octal, but it's typical to have numbers that start with that have a leading 0 be octal. So if you want to write, like 0715, you would write, if you put 0715, this is octal 715. So frequently in many languages, now I didn't look this up. I'm not sure if you put 07, I don't think it'll do this in C++. If you start with a leading 0.
Some languages interpret that as octal.
Now I don't remember. Darn. Can somebody look that up on Google so that we can get this? Octal. Yeah, if in C, I don't think this is true in C++, but I think it's true in assembly language. I know it's true in many assembly languages. But since we don't use octal, we don't do it in PEP 8.
It looks like you can do it in C++.
If you start a constant with 0, is it octal in C++?
Octal numbers, basically.
Octal in C++. You Google octal in C++.
Yeah, we're at c++.com. Yeah.
So that is true in C++. I was
17, you do
you do 017. You would do what?
021.
Yeah, 021. So this is an octal constant. Okay, so I was mistaken. It's also true in C++.
Go to c++.com.
Yeah. Okay. So anyway, that's why I did it like that.
Makes sense.
Okay. So now here's the recipe. What you do is you take your two machines. You see these two separate machines in 7.21a? You take these two machines, and what you do is, because we want to have one finite state machine that recognizes either, we make, instead of making the start state A in the one case and the start state D in another case, we make a new start state. We're going to call it F. And that's our new start state, and then what do? You give it an empty transition from F to A and an empty transition from F to D. Right? Doesn't that make sense that would recognize either one? But now once you've done this, what kind of a finite state machine is this?
Non-deterministic.
It's a non-deterministic. So what do we want to be able to, what do we want to do?
Eliminate.
We want to eliminate the empty transition to make it deterministic, because it's easier to program a deterministic finite state machine. Are you with me? But we have a recipe for doing that. We just talked about the recipe for eliminating the empty. So instead of going from F to A on the empty transition, what can I do?
We need to go from F to B on 0.
From F to B on 0, and then instead of going from F to D on empty, we go from what?
F to E on 1 through 9.
F to E on 1.9.
And F has to become a...
And then what happens is, does everybody see now that figure 7.22a, we've removed the empty transition? Are you with me? But now what do we see? States A and D are what?
Inaccessible.
Inaccessible. And so now when we remove the inaccessible states, we have figure 7.22b. By the way, this is another reason we don't want to have 0.
Because we need it.
Because if we did let 0 have a leading 0 here, then we wouldn't know, it would give us a problem here. So that's how we would remove the inaccessible states. And now this is a multiple token recognizer. Now do you see why it's a multiple token recognizer?
Because it recognizes 2 separate.
Yeah, it recognizes 2 tokens. It recognizes either a 0x or a decimal number. And how do you tell which one you recognized? If you end up in what?
Which state?
Yeah, if you end up in C, you've recognized the 0x. If you end up in E, you've recognized an unsigned integer. Is that clear? Does everybody see how that works? Okay. Well, we have spent so much time on answering the homework, but I think they were good questions. And this. So now what we're going to do next time is we will actually, for your homework on Thursday, you have a program. And so we're going to get back to Java programming on, and we'll do that tomorrow. And we will show how you program a finite state machine, how to do a program tree. And then what will happen is, now, and here's a little previews of coming attractions. So you see, what you're going to have to do is, what is an assembly language statement? It's a group of tokens. All right. So what you're going to have to do is, we're going to have to design a finite state machine that recognizes all of these tokens. You see? It'll be a big finite state machine. So now what we'll do starting tomorrow is we will show you programming techniques. There's 2 different approaches to programming token recognizers with finite state machines. And we'll learn both of those techniques, and then I will recommend one of those 2 for your actual project. Okay? One more question for you?
Just wondering what that was again. Is that for a symbol?
Oh, this one. Yeah, what does this one look like?
It looks like a symbol, but why would there be a final state on B?
Yeah, because see, look. Okay, that was a good question. I was going to wait till next time, but look, this is figure 7.23. This is a multiple. Yeah, let's end with this. This is a multiple token recognizer.
Okay.
But now, actually, as it turns out, it works for this. Because look, what happens is it could either recognize MAIN colon, in which case it did what? It recognized the definition of a symbol.
Right.
Or it could recognize NUM, in which case it recognized a symbol, but not the definition of the symbol. Now, put that in your pipe and smoke it. Is that cool? Mm-hmm. See, so yeah, there's lots of implementation questions involved here. And as it turns out, that one is relevant even to this line right here because of this. And of course, this is not a token up here, so get rid of that. All right? Good deal. See you tomorrow.